Welcome everyone. For today's prep, we're going to keep going with power series. And we're going to start with a few definitions. So the first definition is the interval of convergence. So when we talk about power series, we're going to be talking a lot about the interval of convergence and also the radius of convergence. So the interval of convergence is essentially just the domain of our power series. So we're just giving it a fancy name. And we just want to keep in mind when we talk about the interval, A is the center of our power series. And our power series is always going to be convergent at that center point. Okay, so interval of convergence is really just the domain. And we'll see a couple different examples of what the interval of convergence might look like. Now, the radius of convergence, essentially this is just giving us a measurement of the size of our domain. So you want to think of, when we talk about the interval of convergence, you almost want to think of it like it's a circle. And the A value here is the center point of that circle. So the radius is just describing how big our interval is in some way. And the way you can calculate it, we'll call it capital R, and it's just the width of the interval of convergence divided by 2. So we just take the width of our interval of convergence, divide it by 2. Kind of like when you have a circle, there's the diameter, and then the radius is half the diameter. All right. And a lot of times we'll abbreviate interval of convergence, IOC, and sometimes we'll do ROC for radius of convergence. All right. So when we have a power series, there's a few different options for what can happen with our interval of convergence. So have all the possibilities listed right here. So for our interval of convergence, there's a few different options. It can converge just at, our power series can be defined just at that center point. This is kind of like the worst case scenario. So this is the singleton set of the x values where it only contains one number. And if that's the case, well, our radius of convergence for that would just be 0. So the set containing just one point, well, there's really no width to that. There's just, it's 0 width. The other option is that it could be all real numbers. So it could be the entire x-axis, essentially. And, well, this has infinite width. So in this case, the R value would be infinite. All right, so the other 4 cases here, these are finite intervals. So what the radius of convergence R does is it tells us how far we can go in either direction away from that center point. So the left endpoint for our interval is a minus R, and the right endpoint for our interval is a plus R. So we're centered at that A value, and we can go R distance in one direction from there, or we can go R distance in the other direction from that center point. And what happens is these endpoints, we kind of have to check, because you can have the case where neither endpoint is going to be included in our interval, or only one endpoint or the other endpoint is going to be included, or maybe both endpoints are going to be included in our interval. So the endpoints are something we have to check kind of separately from a lot of our calculations. So these are examples when your R value is positive but finite. And just a reminder, we use parentheses when we want an endpoint to not be included. So if you use parentheses, it means we're excluding that endpoint from our interval. And if we use the brackets, brackets mean we want that one, that we're going to include that one. So if we use the square brackets, the endpoint is included. Okay, so let's try an example. And well, we'll see how these take a while. These problems are a bit lengthy. So we're going to do one example. Hopefully we'll finish it. All right, so let's try this. And before we do get started, there is a little typo here. So we're going to start our n value at 1. Not a big deal. It's not going to change anything. But when n is 0, we get division by 0. So just to clean this up a little bit, we're going to start this at n equals 1. Really not going to change anything, though. All right, so we've got this power series. We've got x minus 5 raised to the n over n squared. So we've got our power functions and then our kind of our coefficient term. So how do we find, and we want to find the radius of convergence and the interval of convergence for this power series. And what this does is, how we do this is with our ratio test. This is what we kind of started looking at in class. So our first step here is we're going to start with our ratio test. So we're going to set it up first, and then we'll do our limit, kind of like we normally do. All right, so what gadget do we calculate for our ratio test? Well, it's that absolute value of an plus 1 over an. And when we do this, it usually is helpful to take an plus 1 and write that first as one fraction, and then next door to that we'll have the reciprocal of an. And then we'll multiply those two things together. All right, so first of all, what's an plus 1? Well, an plus 1, we go to our power series here, and wherever we see an n, we're going to change that to parentheses n plus 1. So we're going to end up with x minus 5 raised to the power n plus 1 divided by n plus 1 squared. Okay. And then next door to this, we're just going to take the original term, but just flip it. We're going to put the reciprocal. So the n squared term will go on the top, and then our x minus 5 power will go in the bottom there. And then as usual, when we're dealing with ratio test, rearrange the terms so you get similar terms grouped in their own fractions. So let's get a fraction for just the powers of x. So we'll have our x minus 5 raised to the n plus 1 over x minus 5 raised to the power n. And then we'll get our squared terms together in their own fraction with the absolute value. And now we want to simplify. So how can we simplify this first fraction with the x's? Well, we have n plus 1 copies of x minus 5 in the numerator, and we have n copies in the denominator. So we're going to be able to cancel things out. The powers are going to cancel, except we're going to have 1 extra in the numerator there. So the first fraction is going to simplify to just x minus 5. All right, what about the second fraction? What can we do there? Well, we know with ratio tests we're going to do a limit. So to help us with that limit, both of these terms have a squared around them, so we can factor off that common squared. So we can write this as n over n plus 1, that whole thing squared. All right, so now we got to deal with this absolute value sign. We don't want to forget about that. So a property of absolute value is that it distributes, it distributes over multiplication. So we can break this absolute value sign up and do just the absolute value of our x term, and then just do the absolute value of that the n squared terms. So we can split up our absolute value there. And that's kind of one of the nice things about absolute value. All right, so one of these terms we don't know anything about. We don't know what x is. X is a variable. It's kind of, well, it's kind of what it usually is. It's an unknown thing. So we don't know if x minus 5 is positive or it's negative. Could be either one. So we have to leave our absolute value sign there. But we don't need the absolute value sign around this n term because we know what n is. N is starting at 1, and then it's just positive integers from there. And then on top of that, we're also squaring it. So this thing is definitely positive. So we can drop the absolute value sign here. So if we clean this up just a little bit more, we end up with the absolute value of x minus 5 times this fraction n over n plus 1 squared. All right. So that's just the setup for the ratio test. Now, we have to calculate the limit of this as n goes to infinity. So now we're ready for part 2. We're going to keep going with our ratio test, but now we're going to do the limit. So calculate the limit, n going to infinity, for this gadget that we just figured out, absolute value an plus 1 over an. And let's write down our simplified version. We went through and cleaned it up and simplified it down. So it became just absolute value x minus 5 times n over n plus 1 squared. So this is what we're going to calculate the limit of. Now, as we do this, it's important to, we have kind of two variables that are showing up here. We've got n and we've got x. As we're doing this limit, x is going to be treated as a constant. And why? Well, because we're doing the limit as n goes to infinity. So we're watching what happens as n changes. So this x term, we're going to treat like a constant. So as n changes, this term, whatever it is going to stay the same. Okay. Well, really then our focus is going to be on this fraction with n over n plus 1. And we're just going to do our usual trick for this one. Pick out the largest power of n in the denominator, and then just divide every single term by n. So we end up with 1 over 1 plus 1 over n squared. And then we watch what happens as n goes to infinity. So that absolute value term is going to stay the same. Remember, we're treating that like a constant. And then this fraction, this 1 over n is a c over infinity form, so that term's going to go to 0, and then everything else is just a constant. So we end up with 1 over 1 plus 0 squared. And if we simplify this, this is just 1 over 1, which is 1, and 1 squared is just 1 as well. So this limit here ends up just being the absolute value of x minus 5. And for a lot of these types of problems, this limit here should have that x term, that absolute value of the x term in it. But all the n terms should be gone at this point because we've calculated the limit now as n goes to infinity. All right, so we've done our ratio test. We've calculated the limit. So now what do we need? Now we're moving on to step 3. And in step 3, we're going to take that limit and we're going to set it to be less than 1. So why are we going to do that? Well, for our ratio test, if we remember back, for our ratio test, what do we need? We need that limit L to be less than 1 for convergence. After all, what are we trying to do here? We're trying to figure out where this power series converges. So we're interested in knowing, when does this thing converge? And so the result that we found from this ratio test, well, we need that result to be less than 1. So we're going to take that limit L, and we're going to set it to be less than 1. So x minus 5 here, we're going to set it to be less than 1. All right, so now once we have this inequality set up with the absolute value sign, we're going to rewrite it as a double inequality. So we're going to get rid of the absolute value sign, essentially. So how do we do this? Because it's hard when we get to more difficult, when we get to more advanced problems and more difficult problems, I guess, we're going to have to like move things in and out of the absolute value sign. So addition and subtraction doesn't work really well with absolute value. So it's best to get rid of the absolute value here. Multiplication, division, not too bad with absolute value, but we're going to have to kind of add and subtract things. So it's better, it's helpful to get rid of the absolute value sign. And so to get rid of the absolute value sign, we're going to turn this into a double inequality. So we're going to keep the x minus 5 in the middle there, and we'll keep that to be less than 1, but then the absolute value gets rid of any negatives. So rewriting this as a double inequality, we take the term that's in the middle, the x minus 5, and it's still going to be less than whatever number was on the other side, but then it's going to be the negative number, the negative version of that on the other side of our inequality here. So we have this double inequality, and then the idea is we're going to solve that for x. All right, so what are we going to do? Well, we want to get x all by itself there in the middle. So right now we have x minus 5. What are we going to do? We're going to add 5 to all three sides of this inequality. All right, so what do we get after we do that? Well, we're going to have x all by itself in the middle. And then 5 plus 1 is going to be 6. And then negative 1 plus 5 is going to be 4. So we're getting close. This is almost our interval of convergence. But it's not necessarily the answer. So we're getting close, but we're not quite there. But we are ready to actually state what the radius of convergence is. So now we're ready for our radius of convergence. So we'll call this capital R. And if we remember, the radius of convergence is the width divided by 2. So this is almost our interval. We just have to see what's going on at the endpoints. We have to check the endpoints. But the endpoints don't really affect the width of this interval. So how do we calculate the width of this? Well, we just subtract the two endpoints. So the width here is going to be 6 minus 4. And then we're going to divide that result by 2. So 6 minus 4 is kind of like the diameter. And then to get the radius, we're just dividing by 2. And if we calculate this, we end up with 2 over 2, which is just 1. So that is our radius of convergence. The radius of convergence here is 1. All right. So now we have to check the endpoints. We're not done, though. So we've got part of our answer, but now we got to get the rest of the answer. We got to see what's going on at these endpoints. So that's the next step. So we've got two endpoints. We've got 6 and 4. So the idea with checking these endpoints is we're going to take each of those x values and we're going to plug them in to our power series. So when we do that, our power series was the sum from n equals 1 to infinity. And if we go back up, it was x minus 5 raised to the power n over n squared. So we're starting with that endpoint 6, so we're going to change that x to a 6. So when we do that, we're going to get 6 minus 5 raised to the power n over n squared. And if we simplify that, that ends up being the sum of 1 raised to the power n over n squared, which simplifies to just 1 over n squared. And this is a recognizable power series. This is just, or not a power series, this is just a recognizable series. This is a P series, and we know whether or not it converges or diverges. And in fact, this one is convergent. So this is a convergent P series. State the p-value, so p is equal to 2, and then state the necessary inequality. So satisfying p greater than 1. All right, so the fact that this is convergent tells us we actually want to include that endpoint in our interval. Now what about the other one, x equals 4? Well, we're going to do the same thing. We're going to plug in to our power series, and that'll give us 4 minus 5 raised to the n over n squared. And if we simplify that, that ends up being negative 1 raised to the n over n squared. And when we look at this, what do we see? Well, we've got this negative 1 raised to the power n. And this is an alternating series. So we can use our alternating series test on this thing. So that's what we're going to do. We're going to do our alternating series test. All right, so how does our alternating series test work? Well, first thing we need to do is figure out what the non-alternating portion is. So the non-alternating piece of this is just the 1 over n squared. And we need the necessary condition for that. So it has to be positive, which it is. So that part checks out. And then there's two things we have to prove for our alternating series test. We got to calculate the limit of Bn as n goes to infinity. So if we calculate that limit, this is just a c over infinity form, so we know that one goes to 0. So that checks out as well. And then we also have to show that Bn plus 1 is less than or equal to Bn. And if we write out what Bn plus 1 is, we've got Bn here, and we're just going to change that n to a parentheses n plus 1. So it'll be 1 over n plus 1 squared, and we want that to be less than or equal to 1 over n squared. And if we cross multiply, we end up with n squared is less than or equal to n plus 1 squared. And that's true. When you take a number and you square it, and then you take the very next number and square that, that's going to be bigger. So, true. And because this is true, it means our original inequality is true. So because all of those things are satisfied, we can say this series converges by our alternating series test. And what did we find? Well, in both cases, the two endpoints ended up giving us a convergent series. So now that we know that, we're ready to state our interval of convergence. So we started with this interval going from 4 to 6. And we can, if we think of this as an open interval here. So parentheses 4 on one side, parentheses 6 on the other side. So we can write it in interval notation. That wasn't quite our answer, though. So what we found, though, after checking the endpoints, is that x equals 6 was convergent and x equals 4 was convergent. So that means our interval of convergence, we want to include those two endpoints. So we're going to use our square brackets. And there we go. So you can see these problems take a little, well, they take a bit of time. And they're a good review for a lot of our other series tests. So the way we're doing this is we're using the ratio test to really get us started. And this gets most of our interval for us. So the ratio test does most of the heavy lifting. Where it breaks down is it breaks down at the endpoints. So we use all of our other tests to kind of figure out what's happening at the endpoints for our interval. Why can't we use the ratio test here? Well, the ratio test, if we try to use it at the endpoints, we would end up with L equal to 1. And that would be inconclusive. So the endpoints, the ratio test doesn't work for, so we have to kind of break out the other tests that we've seen. All right, so that's going to do it for this one. And apologies, I know it went a little long here, but there's really just no way around it. These take a while. So there's a lot of work with these. So we'll practice a few more of these in class over the next few days. And these ones are really good review for all the tests that we've seen. All right, we'll see you in class. Bye-bye.